Hello, this is Britt Caswell with another video on quadratics. I am now getting into graphing. Today's video is on graphing standard form. So you might be wondering, what does standard form look like? Okay, that's an equation that looks like y, or a lot of times they put it in f of x notation, that's okay. Y equals ax squared plus bx plus c. So that is the standard form. Now, with every form of quadratics that you encounter, they have some useful features to them. With standard form, the useful feature is actually this c value. This c value is our y-intercept. So remember, a quadratic, the y-intercept is where the graph crosses our y-axis. So what that means is that x is equal to 0 here. So if I were to plug in 0 to each of the x values here on the equation, that would leave me just with that y-intercept value. So standard form is really nice in terms of getting to that solution. Another cool feature about standard form is this a value. If you have a number here that is positive, your parabola opens up. If your parabola opens down, that a value will be negative. So you can right away see that, like, which direction your parabola will open or close, and you'll be able to see where your y-intercept is. Now, some other really nice parts about quadratics are right here, these green dots. These green dots are usually people's biggest focus when they're using quadratics to solve real-world problems. These are called the zeros. Now, they do have a lot of other names. Sometimes they're called x-intercepts. Sometimes they are called solutions. I usually call them zeros because that's the most common thing that we see. This parabola also has this dotted line that you see right across the middle. That's our axis of symmetry. So remember, for something to be symmetric, that means that I could fold it in half along this axis, and it'll map onto itself. Now, knowing the axis of symmetry is really nice because on the axis of symmetry we'll have a point called our vertex. The vertex is either the highest point or the lowest point on our graph. In this parabola, where it opens upwards, that vertex is the lowest point. So when we are graphing, sorry, my cats are having a great time this morning. When we are graphing in standard form, we're usually looking for what I call the usual suspects. When we graph, we're usually wanting 5 points on our graph for quadratics. That's our goal. Now, some people are really picky and ask for 7. I could tell you how to get the 7 points, but 5 points is usually good enough. Now, 2 of the points that we look for are the zeros, okay? You can get those by factoring. You could complete the square. You could use the quadratic formula. Any of those will get you those zeros. And that's 2 of our points. Another point that you want is the vertex. So you want to find the axis of symmetry and then the vertex. Okay. Now, to find the vertex itself, you plug the value for the axis of symmetry into the equation. Now, the axis of symmetry formula is actually really easy to find as well. So to find the axis of symmetry, you say x equals negative b divided by 2a. So that'll get you the x value for your vertex, and then to find the y value, you plug that into the equation to get y. Our other really important point is the y-intercept. Like I said, with standard form, it is so easy to see it just because it is your c value. Now, just a minute ago, I told you guys that we need 5 points in order to graph something, right? What we have done here is we've actually described 4. So the way that I usually get my fifth point is I reflect the y-intercept across the axis of symmetry. So the y value will stay the same, and then the x value changes, and that gets us our fifth point for our nice little u. Another way to generate 2 more points, so say you need 7 points for some reason for a more accurate graph, you can take the a value, and that a value describes how far up or down you go when you go 1 unit to the left or to the right. So say, for example, I have a parabola who has a vertex at the origin, and say my a is 2. What that's saying is when I come 1 over, I would go 2 up, and then I'd go to the side again and go 2 up, and that would get me part of my u here. Now understand, with that a value trick, you can't use it more than once. So if I go another 2 over, it's not going to, or I'm sorry, another 1 over, it's not going to go 2 more up. Okay, parabolas don't work that way. So it only works for the first little section right here. And with that, that's all that we need to know in order to graph in standard form. So let's go ahead and let's try an example. So this example is in standard form, because the exponents are counting down. So I always start by setting room aside for my graph. So I know I'll be graphing over here, and then I find my usual suspects to the side here. Often I find it's easiest to kind of list off my usual suspects and then solve them out piece by piece. One of my biggest mistakes when I graph is I'll graph them piece at a time, and then when I get to the end, my scaling's off on my graph. So it's usually easiest to kind of just list off here, and then once we have all the values that we need, then go through and graph it. Alrighty. So here are my usual suspects, kind of laid out here. So I'm going to start with my zeros. Now with quadratics, there's a lot of ways to find the zeros. Okay, if you're using my quadratics big picture, it's all the stuff listed at the bottom. So you can factor it, complete the square, or the quadratic formula. In this case, I specifically found a problem that you can factor, just because with my students, that's where they're at right now, is they haven't learned the other tools. So I'm going to factor to find my zeros. So the first thing I notice is 3, 6, and negative 72. Those have a common denominator. Or I'm sorry, a common factor. That is 3. So I'm going to factor that GCF out of my expression. So 3x squared divided by 3 is x squared. 6x divided by 3 is 2x. And negative 72 divided by 3 is negative 24. Now notice that that 3 is my a value, okay? So when this parabola opens up, I know it's going to open upwards because this is a positive 3. And I know that it's going to be kind of narrow because when I move 1 to the side, I'll be moving 3 up as well. So then factoring up this bigger set of parentheses, I set up my double bubble. I drop down my first sign. To make a negative 24 here, my signs have to be opposite, so I'm going to put in a minus. And then I have to think about what multiplies to make 24 that subtracts to make 2. And that is 6 and 4. So this portion here, now we've factored it. What we need to do is we need to use the zero product property to find the zeros. What that property says is if this expression is equal to 0, so if y here was 0, then one or both of the things being multiplied must equal 0. So that allows me to take these two sets of parentheses and set each of them equal to 0. So I have x plus 6 equals 0, and x minus 4 equals 0. So if I go to solve that, I get negative 6 and a positive 4 for my zeros. Now if you're good with the zero product property, you could usually stop right here and just mentally math recognize that you flip the signs. Alrighty, so now for the axis of symmetry. So to find the axis of symmetry itself, I'm going to be using the formula x equals negative b over 2a. Now, another thing you can do is you can find the halfway point between those two zeros. Okay, that's another option. Often it's easier just to look at that and find the halfway point. But if you have fractions or decimals, this is usually the way to go. So I say x equals negative. Oh, I need to know my a and b value. So if I come here, my a we discussed already is 3. My b is 6, and my c is negative 72. So when I plug in negative b, I have negative, and my b is 6, over 2 times my a value, which is 3. So that's negative 6 over 6, which is negative 1. Sorry, that looks like a 7. There we go. So when I do eventually draw my graph, which I don't know my scaling yet, it's going to have to be some kind of big scaling. I can tell because that C is so big. I'm going to have an axis of symmetry here at negative 1. So just to the left of that x-axis. Now remember, the vertex lies on the axis of symmetry. So I could take that negative 1 and just plop it right there for the ordered pair for my vertex. And in order to find the y value for my vertex, I need to plug it into the equation. So I'm going to take our original equation, and where the x is, I'm going to write a negative 1. Now, it's important here when you're doing this to make sure that you're using parentheses. Especially if you're a person that's really reliant on your calculator, because the calculator will mess up if you don't have it. Alright, so here, negative 1 squared is a positive 1, times 3 is 3. 6 times negative 1 is negative 6, and then there's a minus 72. So my y value for my vertex would then be, let's see, that's negative 78, so negative 75. So I know when I go to do my graph, I'm not going to be counting by 1s or 2s because I need to go all the way down to negative 75. So I might make my scaling something a little easier, maybe like 10s or something like that. So then looking at my y-intercept, remember my y-intercept is my c value. So my c value here is negative 72. Now to reflect it, I know that that negative 72 stays the same, but then we have to think about the distance that we need to reflect. So if my axis of symmetry is negative 1, it's right here. The distance from the y-axis to that negative 1 is just 1. So I'm going to need to go an additional 1 over in order to reflect properly. So that'll be at negative 2. We'll be able to see that one a little bit better when we actually go to draw our graph. So that's it. Now we have our usual suspects and we are ready to go. This is usually the quickest part of the graph. So because my numbers are so big, I am going to be counting by tens. So I'm going to write that up here just to remind myself my scale is by tens. So then I'm going to go ahead and draw my little tick marks in here. Probably should have done that in advance, but that's all right. Alrighty. So I just kind of go down the list. So my zeros are at -6 and at +4. So -6 is about here. Now remember, when you draw in points on a graph, it is usually kindest to whoever's reading your graph to label what those points are. So if you notice, as I'm filling in these points on my graph, I'm actually labeling the ordered pairs. So there's my zeros. So now if I go to my axis of symmetry, it's at x equals -1. So -1 is really, really close to the x-axis, or sorry, the y-axis. So it looks a little skewed here. Remember, when you write out the axis of symmetry on here, it's an actual line, so you need an equation for that line. That's why I wrote x equals -1. And then my vertex is at -75. So there's 10, 20, 30, 40, 50, 60, 75. So I'm way down here at -1, -75. All right, so then, sorry, my pen's acting up this morning. My y-intercept is at 0, -72, so that's just after this dot. And then if I reflect that, I'll have another dot right here at -2, -72. And then you just draw your U shape between all of these points. Hopefully a little straighter than mine. Now remember, parabolas do continue on for forever, so at the end of these U's you might want to draw an arrow just to remind yourself that they go on for forever, but a lot of times graphs don't bother showing that. But really they do go on for forever. And that's it. That's how you graph in standard form. The more that you do this, the faster it goes. So don't fret that this is a 17-minute video. Until next time.